Welcome back. Session 3 is still, we have spoken of scientific setup, scientific experimentations, explorations, the variables of interest, the independent variable, the dependent variable, control variable. We talked about the sample size. We talked about quite a few things in terms of the normal distributions and the way that the small sample versus the large sample relate together. And then we spoke of, generally speaking, the mean of samples that we take from experimentations. And then we related that to the normal distributions in the previous recordings. Now I would like to continue that, and this time I'm going to go into the null hypotheses, and let's see what it means. Before that, I want to remind you once more about the normal distribution. Intentionally, I made this normal distribution to be symmetrical. As you can see, this is actually a station around 0. This is a y-axis. I shifted the mean so that I can have the basically the normal curve station on 0. It is symmetric. This plus and minus 1 means plus minus 1 sigma, plus minus 2 sigma, plus minus 3 sigma. And if you take a look at this with the center, that would be here, which is mean or average, and then plus minus sigma, you are going to cover 68% of the population, which is nice, not bad. 68% is approximately 70, I would say, just to forgive ourselves on this one. Then if you have plus minus 2, you are going to have 95%. And plus minus 3, it's 99.7% with a little bit of a white space that you don't see. Hopefully you can see that here. And they are not accounted for. So this is plus minus 3 sigma, 99.7%. We would consider this a very nice inclusion, but this might be a stretch for any statement. If you take a look at the middle one, you have 95%, so it means that the area from infinity to this one and from this area to plus infinity together is going to be 5%, which is 100 minus 95 equal to 5%. So this plus this is supposed to be 5%. So I could potentially say that this is 2.5%, and this is going to be 2.5%. So I want you to keep that 2.5% in mind. If I wanted to actually look at the system symmetric and then look at the two tails of it. We talk about the tail in a moment. But 95% is a significant threshold, is very nicely inclusive. So if your statement is true 95% of the time, then your statement is very strong. 95% is not bad. So let's review once more. This is another way of looking at it. The center, the mean is here, 150. 1 sigma, 2 sigma is here. 1 sigma, 2 sigma is here. 2.35 is going to be the area between 3 sigma and 2 sigma. And 0.15 is going to be from infinity to this area. If you add these two up, it's going to be 2.5. This is also going to be 2.5. So just keep that in mind. Let's take a look at a simple statement. Everybody, let's say it this way. A person is, I want to delete the word everybody. I just want to state it a little bit more appropriately. A person is innocent until proven guilty. What does that mean? If you take a look at this curve that we just spoke of, or even this curve, doesn't matter. The numbers really doesn't matter. So if you take a look at that, we could potentially measure innocence. And there may be people who have never had any brush with the law office and nothing wrong. All the rules and regulations they have followed. They haven't stolen anything. They didn't crash to another car. They didn't have an accident. They didn't have any ticket. They were just a nice driver, no speed ticket, nothing. And they didn't kill anybody, right? So, and you could potentially say there are some people in the society that are really honest a hardworking individual, but they may have gotten a parking ticket. There may be somebody who might have gotten a speed ticket. But still, this person who has received a speed ticket still is an honest man or honest woman, for that matter, honest person, I would say. So I'm going to say that when I say 95% of my population is honest or innocent, I'm actually quite inclusive. I'm going to have a huge population. I have an umbrella, I have a tent, and I'm going to include as many people as I could from my little society, a village, a city, a country, a continent. And then there will be people who are outside of this tent. And obviously those people might have committed something, a little bit of a serious crime, such as stealing or perhaps even hurting and abusing someone else in their lifetime. So this is 2.5, this is 2.5. And we will be happy if we are 95% inclusive. If this is more than 2.5, maybe 3%, then we say, wow, no, hold on. Something is happening. Something is wrong. Something is not working with this society. You are taking away a slice of my 95%. If you say 3% and 3%, that's 6%. This is 94. If you say 5% and 5%, that would be 10%. This is 90%. You are taking away a slice of my tent, of the people who are in the tent, and inclusive. So we are going to actually consider this as a significant threshold. And if in your experiment, anything below 2.5 on this side, above 2.5 on this side, in this case, 2.5, of course, is so basically below 2.5 is still. So if you are here, the area underneath is going to be less than 2.5. Then we are going to say, yes, the tent is working. The inclusiveness is working. And that's what we want to achieve. So if the statement has truth in it, then the tails are supposed to be less than 2.5 each, or potentially summed up together at 5. I can live with that, 95%. And we are going to have one left tail and right tail in a moment. So with that in mind, with the fact that if I make a statement, the truth and the strength of the statement is going to be seen as 95% or more, and anything excluded is going to be less than 5%, 5% or less, I'm going to be a happy person. The statement is going to hold quite strongly. So when we spoke of null hypotheses, we said you have H0, we call it H0, we call it H0, we call it H null, and then HA, A stands for the first letter of alternative. So this is the null hypothesis, and this is a alternative hypothesis. When we say null hypothesis, it means, listen, my society, my people, my village, my city, everything is really a decent city. And if you go and take any sample of any kind, however you like, the difference between the two samples are insignificant. And that's a very important observation. If you say, listen, go to the left, go to the right, pick up anything, pick up a random, and mix up with the gender and the race and the age and everything else. And if you have done a proper sampling, which, as I said, many of the parameters, variables have to be discussed in that process, then what I'm trying to claim is that the two samples show little to no significant difference. That's what it means. That's what the null means. And then the alternative means, no. The difference is significant. Let's take a look at an example. Do smokers weigh the same as non-smokers? So null hypothesis, the average weight does not differ. And the way I'm going to do it, in the blue curve, I'm going to establish my sample, and the sample is going to be H0. And keep in mind, these are smokers. So basically, I could do many things. As we discussed in the normal curve in the previous session, you could potentially do this sampling in many ways. You could have 2,000, 2,000, 2,000, 2,000 many times. You could raise the size of your sample, many things that you want to do, and eventually you get me this curve that is indicative of the weight of smokers. And then there is a black line. This black line is about the non-smokers. And this is the mean weight of the non-smokers, and that's going to be this. When I say this is non-hypothesis, and I say it does not differ, it means that the average weight of non-smoker and a smoker, the weight has nothing to do with their smoking. This is what we are trying to say. And at the same time, pictorially, what does it mean? It means that the blue curve and the black curve are almost identical, with the same mean or average, with the same standard deviation, okay? Almost. And if there is something significant, then there is a red alert. What is it? Alternative hypothesis is the average weights differ based on whether you're smoking or non-smoking, which means smoking could potentially have an impact in your average weight. Okay, so the way we are going to do it, the blue is going to be this one. The blue is going to be, I think this one potentially is going to be 0. Perhaps we made a mistake. And this is going to be the null hypothesis. Smoker, let's keep that. So this is supposed to be 0. And this is the non-smoker. This is the black. This is what is supposed to be in the null hypothesis. And as you can see, the black curve is significantly different and drifted from the blue curve. In this case, just the mean. It could be the standard deviation, or it could be both. Okay, so that's going to be a red alert. If this is going to be true, if there is any truth in this, then I have to investigate. I have to see why and what the cause of impact of a smoking or non-smoking has into the average weight of the person. So are we okay? Do we settle on this? And let's settle on this, that there is a null hypothesis and there is an alternative hypothesis, and these two are supposed to be mutually exclusive. Then we have another example. I just wanted to bring this example to your attention once more. And the statement we are going to make is this: the people who hold driving license are 18, or either 18 or years old or older. The people who have driving license are either 18 years old or older. That is nice. That is going to be my null hypothesis. And as a matter of fact, when you take a look at the alternative hypotheses, and that says that there are people younger than 18 years old who are going to have a driving license, obviously that doesn't pan out. The rules and regulations stops anybody who wants to obtain driving license, of course, in North America, and is less than 18 years old. As you can take a look at that, you will see that there is a strong yes, almost unanimously in the null hypotheses, and there is a strong no, almost unanimously, or empty set, almost unanimously for people who are less than 18 years old. But the truth of the matter in real life is that it's not going to be a clear cut like this. This is clear cut because the government enforces it. There is nothing you can do. The government says either you are 18 years old or above, and then you can apply, or if you are younger, you have to wait. There is an enforcement behind it. But when we talk about, for example, when we talk about smoking and weight, who is going to enforce this? There is no law. There is no rule. There is no action that is going to force this relationship to happen. And therefore, this is not going to be just yes and no. This is not going to be 0 and 1. So what is happening is that it's going to look like something like perhaps a normal distribution, where we are going to have, as we spoke of, we are going to have areas that might be quite in the extreme sense. Okay, so there is nothing in the 18 years old and above having driving license, and I actually rephrased my statement. I said those people who have driving license are going to be either 18 years old or above. You see, I changed my statement from the previous recording. You have to be sensitized about what we are trying to do and what we are trying to say, okay? With that in mind, as I said, real life problems are not really clear cut. There is no enforcement. There is no police officer who is going to actually enforce it. And many of the things that we are going to discuss and understand are going to be following potentially normal distributions, and they are not going to be clear cut, such as yes, no, 0, and 1. So if you take a look at this, I have a null hypothesis. For example, the innocent people with designated standard deviation. And then I have alternative hypotheses with designated standard deviation. The height doesn't have to be exactly the same, by the way. It could be smaller, it could be sharper. As I said, when you have two cases extremes, such as yes, 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 and then no, 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 and then the shape is not going to be like this. So the shape is made like this just for the easier understanding of what it means. So you do have a hypothesis, a null hypothesis, and you also have an alternative hypothesis. You have mean and you have mean. They could be different. Of course, I'm going to discuss that. And then you have a standard deviation and a standard deviation. Don't worry about type 1 error and type 2 error, false positive and false negative. We will talk about them later down the road. So what is happening is that you have a null hypothesis, and then you have an alternative hypothesis, H0, H1, H0, HA, doesn't matter, okay? If you take a look at this, simple example that I said, a person is innocent until proven guilty. You don't simply go and prove someone to be innocent. What's the point? The population is so proven in the past centuries, thousands of years, that humanities are decent species. They don't want to hurt each other. They don't want to steal from each other. They don't want to kill each other, right? And they are supposed to be honest people, honest species, right? So you don't just go and grab someone in the middle of the street and say, I want to prove that you're innocent. You see how crazy it looks like, it sounds. But if there's something that has happened and you do have an evidence, you would like to basically take that person to the court and then provide the evidence and prove beyond reasonable doubt that the person is guilty. So with that in mind, I want to alert you to something. The fact that you have a null hypothesis, you don't spend much time, most of the time, you don't spend time on the null hypotheses. You spend time on the alternative hypotheses. It's a lot more meaningful for such a vast and inclusive rule. Maybe even more than 95% of the people in the village and city and country and continents are actually innocent. You don't want to spend resources to prove them that they are innocent. But if there is someone who is guilty, you do spend resources, and for that individual, although it may take a couple of $1 million to prove that this person is guilty, keep in mind that couple of $1 million is a lot cheaper and smaller than proving the entire society to be innocent, okay? So if you take a look at this, I'm not going to focus much of my attention on the null hypotheses. Rather, I'm going to pay much of my attention on the alternative hypotheses, okay? Now, as I said, as an example of an 18 years old and above driving license, my HA would be that the mean of my sample, if it exists, is supposed to be less than 18 years old. I said my null hypothesis is going to be 18 years or above. So it's less than or equal to 18. Sorry, more than and or equal to 18. For the null hypothesis, it is more equal 18. So my HA would be less than 18. Okay, so that's what's going to happen. When I say that a person perhaps after 70 years old does not have a driving license, and in that case my statement is going to be different, but my mu is actually going to be basically greater than 60, 70 years old. So this is another alternative. Keep in mind that all the time we are looking at the alternative hypotheses. Remember, we moved away from null hypotheses. We did all we could to express it. And upon expressing it, we had done all we could to express the alternative hypotheses. After we have done all of our efforts and exhausted that to express what the alternative hypothesis is going to be, our attention is here. Our attention is on alternative hypotheses. Now, do you remember that we said that the strength of the normal distribution is in the fact that 95% is inclusive, and 2.5 here and 2.5 there, and even less would be even more beautiful. So if you have 1% on this side and a little bit blue here, and 1% on this side and a little bit blue here, then your statement is closer to truth. Then your statement is stronger to validate and accept as the universal truth. But that is at the same time, if this part is cutting a slice from my blue space, and this is going to be white, and then it's going to be white here, and then it's going to be white here, then I'm going to be in distress. Then there is a red alert. You are actually eating into my base. You are eating into my trust, and I need to actually go back and fix it. So this is what is the basically alternative hypotheses. If in the alternative hypotheses, you get alpha divided by 2, alpha divided by 2, alpha being usually 0.05, which brings us to this number of 2.5, as I said. If this is the case, right, then it means the alternative hypothesis has a strength, has truth in it, has some value in it. It is very bad for an alternative hypothesis that is supposed to be mutually exclusive with the null hypothesis, and suddenly you see that the alternative hypothesis seems to have truth in it, and it has a weight of correctness in it. Because what happens is that when you examine the alternative hypotheses, you see that this is either 2.5% or less, which means this is inclusive. This is inclusive. It's the null hypothesis was supposed to be inclusive, 95%. Now you are coming back and you're telling me that HA, the alternative hypothesis, is more than 95% inclusive? Something has to be wrong with the null hypothesis. So if this is less than 2.5 and this is less than 2.5, then you have to reject the null hypothesis and pay attention to what the alternative hypothesis is telling. This is called two tails. This one, as we said, about 18 years old, this is left tail, and this is called right tail. Now, we have agreed happily on the 5% threshold. So this 5% threshold could be 2.5 here and 2.5 here, or if you want to do on the left on a left side, I'm okay if you want to grab 5% and leave me alone with 95%. If you grab 5% and leave me alone with the 95%. But if this is alternative hypotheses, I'm not okay. So if you say that this is 4.5%, that means there is a truth in alternative hypotheses. There is something correct about the alternative hypotheses, and there is something wrong with my null hypotheses. So keep that in mind. So if this happens, alternative hypothesis becomes strong, null hypothesis becomes questionable. And this is the zone where you are going to reject the null hypothesis. So again, another example that is going to combine them together. Here is mu, the null hypothesis is 23 for some of the experiment, and HA alternative is mu is not equal to 23. So when I say 18 years old and driving license, I mean, okay, 19 years old, 20 years old, do they have driving license? So if my statement is limited to 18 years old only, then my argument would be 16 years old, 17 years old, 19 years old, 20 years old. So that's what I'm going to say. If you are focusing on that 18 years old, anything other than 18 years old would be important. And as such, I'm going to actually look into the two tails. If it is greater than or equal to 18 years old, such as this, then the mutually exclusive statement would have to have the mean to be less than 18. Again, I'm referring to that experiment where I was talking about the driving license and 18 years old. This is, of course, 23 coming from a different experimentation. And this is going to be basically the left tail, so we call it the left tail. And this one is going to be basically right tail. This one, we are going to say anybody less than 70 years old is allowed to drive. And therefore, anybody above, I say less than or equal 70 years old, and there is anybody above 70 years old are not allowed to drive. So this is going to be the right-hand case. Once again, whether you are considering left tail test with alpha is equal to 5%, right tail test for 5% alpha again, or basically two tail test where you are going to divide the 5% to 2.5 and 2.5, you are an area that you need to consider fail to reject the null hypotheses. And the way it works is that if you are going to be more than 2.5 here and more than 2.5, this is the area I'm talking about. If you are 2.5, you are actually eating into the slice of the alternative hypotheses. And that means that alternative hypothesis is not as inclusive as it is supposed to be, okay? Once again, this is just a refreshment, alpha divided by 2, alpha divided by 2. We are talking about the area, the blue area. We are not talking about the amplitude or the volume. We are talking about the blue, the blue area, and that's going to be my critical value. And the critical value, as we spoke of, is going to be 2.5% and 2.5%. Typically speaking, we say that this is going to be the center, this is going to be the mean, this is going to be the average. And if the average is something above, you basically shift it to 0. As we spoke before, the amplitude is not supposed to be more than 1. If it is more than 1, it means that your curve is not normalized. You must normalize it because this is supposed to be a representative of probability, and probability cannot be more than 1. This is the probability, and the area we are trying to look into is actually the probability. The summation of probability from infinity up to here, from minus infinity up to here, from plus infinity up to here, and that's what it is. So this is a two-tail test, and this is mainly, as I said once again, we are actually referring to alternative hypotheses. If this is less than 2.5, equal or less than 2.5 on both sides, then there is a truth. A strong statement has been made in the alternative hypothesis. If this is 5% and if this is 5%, 10%, then I would say alternative hypothesis is not as strong as it's supposed to be, right? So I need you to keep that in mind. Once again, we are going to take a look at this normal distribution. If you have, if this is about the, this entire curve is about the alternative hypothesis, by the way. And if you have basically 0.25 and above, if you are anywhere in this between, you are actually deleting, eliminating the strength, weakening the strength of alternative hypotheses. But if it happens to be that you are less than 0.2, less than 2.5% on either of the side, then it means that, listen, the alternative hypothesis not only covers inclusive 95%, this seems to have even more inclusive than 95%. perhaps by the time you calculate everything, it could potentially be, this is 0. This is 7, 0.7, 0.7, 1.4, 1.4, 100 minus 1.4. That's going to be 98.6. 98.6 inclusive? That's really fantastic. So that means the alternative hypothesis has a lot of strengths in it, and therefore you would reject the null hypothesis. Now, we have a special terminology. We say reject the null hypothesis, or we say fail to reject the null hypothesis. Fail to reject the null hypothesis means accept it. Fail to reject, they are going to cancel each other. So reject the null hypothesis, fail to reject the null hypothesis. So that's what we are going to do. This is, once again, is going to be a reinforcement of the topic at hand. Now, in the next session, I would be talking about the p-value and the way we are going to calculate the p-value. I'm going to bring some examples to the table, and you are going to make a decision whether a null hypothesis is going to be valid, acceptable, or you are going to reject it. So when we say accept, it means fail to reject null hypothesis. Thank you, and stay tuned for the final episode in this session, where we will be talking about the calculation, and hopefully with that we close the discussion on the scientific experimentation, followed by a lab that I will be recording and providing to you shortly. Thank you.